is prove there is no greatest odd integer. And what we say is we use the contra argument that there is a greatest odd integer, and we will call that n. So if we start off with n as being the greatest odd integer, we know that n must be in the form of 2k plus 1. So if I try adding a number to this, so if I add 1, I get 2k plus 2. That's alright. If I try adding 2 to it though, I get 2k plus 3. And 2k plus 3 can be factored out to 2k plus 2 plus 1. And this part is in the form of a 2 to the value of some number. So we've got 2n plus 1. This is an odd number, and it is an odd number found by increasing n, and we found it by increasing n by 2. Because of that, 2n plus 1 is greater than n, so n is not the largest odd integer. Prove that if n squared is even, n squared is even for all even n. Okay. Now our assumption is that we can find the contra-example. Now the contra-example of this is to say what would actually say this is wrong, and that would be to say that we can find an n squared is even for an odd number. That's what we're going to try and find. So we set up our values, and we're going to say n is equal to some 2k plus 1. So we now do k squared, n squared, which is 2k plus 1 squared, which gives me 4k squared plus 2k, 2k, 4k, plus 1 times 1 is 1. And like we saw earlier, this first part I can factor out as being something like 2m plus 1. We can factor out a 2, which is odd. So this last one is a classic proof. It's actually the proof that could have got you killed in ancient Greece. The Pythagoreans, I think it was, who they had a strong belief that every single number could be written as a rational. It could be written as a fraction. And we actually now know that, strangely enough for them, the square root of 2 is irrational. Hold on a minute. Okay, there's a guy called Hippasus he was a group of the Pythagoreans, a school of Pythagoras, and he came up with supposedly this sort of proof of why square root of 2 cannot be written as a rational number. For such works, the Pythagoreans apparently turned him upside down into a barrel and drowned him. So sometimes being the biggest brain in the room isn't necessarily the best thing in the world. So we've got to try and prove that this is irrational. And the way we do it is we turn around and say, well, square root of 2 is rational. Sorry, the kids are moving. So what we need to do is we take the contour example. So we say the square root, let's do it in blue, square root of 2 is equal to p over 2q. Now there's 2 steps in this proof. We now turn around and we say, let's square both sides. And then we carry on down to cross multiply. We've got 2p q squared is equal to p squared. From the form, we now know that p squared is even. Okay? So now, in the next step, we're going to deal with p as being an even number in the form of 2k. So we go back and do much the same thing again. We've now got the square root of 2 is equal to 2k over q. And once again, if we square it, we get 2 equals 4k squared over q squared. And if you rearrange so that q squared is equal to something, q squared equals 4k squared over 2, which simplifies to 2k squared, which again shows that q squared is even, which tells you that EQ is even. Okay, the only way to get an even number by squaring is by having an even number. So by proof, our proof statement is to say, now that P over Q is 2 even numbers, so Q equals 2 over L, 2 P over 2Q, we have a common factor so both numerator, K and L. We have a common factor. Because they've got a common factor, they can't have been a rational. P and Q couldn't have been the smallest integers to solve this problem. Numbers in the fraction. You can go round in the loop to lead to the situation that therefore both P and Q can't be an integer, because if the smallest numbers square a fraction, they must, to be rational, these must be the 2 smallest numbers. There must be no common factor between P and Q. So that now leads to, therefore, the square root of 2 is not rational. Cannot be written as 2 integers with no smaller fraction. Okay, so there's the next one. Do the primes one. Let's do the primes one quickly as well, just so you've seen them through. So the black one, so prove that primes, there is no maximum prime. P n. We make the assumption that there is. Pn. So we assume there is a maximum prime Pn. Now we can write numbers as products of primes. So what we're going to do is we're going to say that there is a number n which is the product of the first prime, i.e. 2, times the second prime, i.e. 3, times all the primes up to Pn. That gives me a number which has all these numbers. n as it stands would divide by every single one of these primes. That would stop it being prime. But if I add 1 to this number n will not divide by any prime number so far. And the reason we know that that won't happen is because P1, which is 2, times a list of odd numbers is even. Okay, so the product of all prime numbers will be even. This number does not divide by anything else, so if I now add 1 to it, I haven't got a number that will now divide by 2. So this n is odd. And because it's odd, it must be a new prime number. If it's a new prime number, that means that Pn does not exist. So therefore, we go on to say that hence there is no such thing. No largest prime.